In our discussion about electronics, we want to talk about probably the most fundamental piece of electronics that there is, and that would be what's called the NOT gate. So the NOT gate is a piece of electronics that if you apply electricity to it, to its input, no electricity comes out of its output. And if you do not apply electricity to it, then to its input, then electricity will come out of its output. So the question is, how did this piece of electronic get designed? And what we have here is, this is basically a wire that electricity can travel along. This symbol here, where we have a line with 2 wires coming into it and a third wire as a controller, this piece of electronics this is the schematic for a transistor. So a transistor has this property to it. If you apply electricity along this line, then any current coming along here will be able to pass through and go down this line, if there's electricity applied here. If there is not electricity applied here, then it's like this path cannot be taken. So the electricity source that's coming in through here will somehow try to get to ground. That would be its goal. And if electricity was applied to here, it could find its way to ground. If no electricity is applied here, then the electricity would have no choice but to go across this resistor and then out that path. So from the point of view of this piece of electronics, if we have a constant source of voltage coming in here all the time, and we have a choice, this is our input, we have a choice to apply electricity here or not. If we apply electricity here, then this voltage will go down here and therefore not go out here. So applying electricity here means no electricity comes out of here. If we do not apply electricity here, then the electricity that's coming in through the top, if we do not apply electricity here, then the electricity coming through the top will have no choice but to go out this way. So whatever we do here, whether we apply electricity here, the opposite will happen over here. So, this invention, this thing, the transistor, it's a very, very, very famous invention in the 1930s. It was invented here in New Jersey, along with other things that were invented in New Jersey, like the light bulb and major parts of the internet. The transistor was invented in New Jersey, and there was a team in Homedale, New Jersey. This is actually the water tower. If you've ever been to, this is by exit 114 on the Garden State Parkway, a couple blocks off the parkway. This is on the property of Bell Laboratories. And this is what a transistor used to look like, probably back in the 30s and maybe 1940s. They look different now. But this is their water tower on their property that looks like the transistor which they invented. And there's one path in, one path out, and then one controller. And what's up here is the electronics that allows that functionality that we just described before. So the thing I just wanted to make sure we understood is that this NOT, what we're going to call a NOT gate, has electricity coming into it. And then somehow if you have electricity coming into it, then there's no electricity going out the end. So the question goes, where did the electricity go? The electricity that was coming in. And the other one that looks a little bit more magical is when no electricity comes in, then all of a sudden electricity appears and starts going out the end. And where did that come from? And where it came from was the voltage source coming in through the top and going out this way. So what we're going to do going forward now is we're going to take this piece of electronics and we're going to symbolize it with this triangular symbol with a circle on the end. So the triangle with the circle on the end. The circles now going forward are going to mean that whatever the value of the input is, like if the input is 1, this will flip it to 0, and if the input is 0, this will flip it to 1. So all this is really doing is just saying the current is going through this thing and then being flipped, whatever its value is. So we're going to refer to this as a NOT gate. A NOT gate means Whatever value comes in, the not of it, or the opposite of it, is what goes out. So instead of drawing this, because this will take a while for us to draw, we're just going to draw this symbol. So when you see this symbol, it really means this electronics is what's inside of it. So if a 1 is coming in here, it means a 0 is coming out of here. So yeah, the difference between electrical engineers and computer scientists. Electrical engineers call this electricity coming in and no electricity coming out. And computer scientists say a 1 here and a 0 there. 1 means electricity, 0 means no electricity. And then here's the version, if we put no electricity here, then the electricity coming down here has no choice but to come out. So a 0 going in here is a 1 coming out of there. So that ends up being our NOT gate. And like I say, this is going to be a notation we're going to use instead of drawing this. Now we'll still go over some more electronic components that we could build. So for example, if we wanted to do what we're going to call a NOT AND gate. So a NOT AND gate would be a gate where if we wanted to have the electricity coming in through the top, in order for it to get to the ground, we would have to apply electricity to both of these transistors. That's the only way the electricity could flow through to the bottom. So if this one is a 1, we're going to start talking like computer scientists now. If this is a 1 and this is a 1, meaning electricity is being applied. If this is 1 and this is a 1, this is now a device with, this is now going to be a device with 2 inputs and 1 output. And we're just going to pretend that this and the ground are not part of the picture. So there's going to be 2 inputs and 1 output. So that symbol signifies this piece of electronics. And if this has electricity applied to it and this has electricity applied to it, then this electricity will find its way to ground and therefore not come out here. So if this is a 1 and this is 1, then this is a 0. And under any other circumstance, if there's a 0 on any one of these or both of these, then electricity will come out of here. So the truth table, if you've heard that expression before, for this gate is the 2 1s produce an output, the 2 inputs being a 1 produces an output of 0. Any other input combination will produce an output of 1. So it's like asking, are these 2 both on? And if so, flip the answer. If they're both on, then the answer becomes false, otherwise the answer becomes true. So this ends up being called a NOT AND gate. Okay, and then we could also do a similar piece of electronics for a NOT OR gate. So what we're going to do in the NOT OR case is we're going to not have the transistors lined up sequentially, but we'll have them in parallel. So for the electricity to get from the input source down to the ground, it could go one of 2 ways. It can go along this transistor and down, or it can go along this transistor and down. As long as it can go through either one and get to the ground, then we'll have no electricity coming out of here. So if the inputs now for this electronic device was 0 and 0, then, like in this case, 0 and 0, then the electricity would come out of here, but in every other case it would not. So a 0 and 0 input would produce a 1, and all other input combinations would produce a 0. So that ends up being called a NOT OR gate. So what we can now do is start taking the NOT AND and the NOT OR and the simple NOT gate and just plug them together and start making new gates. So for example, if we take a NOT OR gate, so that we're asking, are these two bits both 0? And if so, a 1 will come out of here. And then flip that. Then this would be, these 2 gates put together would be equivalent to an OR gate. So what we're really saying at this point is either one of them. This gate alone, we were saying if both of these were on, right, then the electricity could flow down to the bottom. This would be off. Now we're saying if both of these are on, then we'll flip this and turn it into being off, right? So for example, if this is a 0 and this is a 0, then the output of this will be a 1, which will make the output after it flips to the other side would go back to 0. In all other cases, it would be a 1. So if either one of these was a 1, then the output of this would be 1. So this is a gate where if the input and the output are both, if either one of these is on, then electricity comes out of here. We could do the same thing with the AND gate. We could take a not AND gate and then take its result and do a not of it, and this becomes an AND gate. So for example, we said that for the not AND gate, we said that if both of these were off, then the output would be on, and then we could flip that output and it would become off. So basically all we're doing is we're taking the gates that we can make together with the electronics we had before and then plugging them together to make new gates. And we could also do 3 inputs and 4 inputs and 5 inputs and so forth. Okay, so now what we're going to do, now that we have some of these basic components, what we'd like to do now is we would like to take those components and make new electronic components. So here what we're going to do is we're going to have a 2-input chunk of electronics. What we're going to do now, this 0 means there's a NOT gate in front of here. So we're going to put like a NOT gate on one of the inputs into the AND gate and another NOT gate in front of the input onto the AND gate. And here we're going to have one of the inputs knotted and the other one not. Here we're going to have the top one being not going straight in and the bottom one being knotted, and then the last one nothing. The inputs go directly in. So if we just, and then these lines, the line in green, which I colored in green to mean it's currently equal to 0, that would be this input, right? These are all the same inputs. And this red one is going to be this input. Goes into the bottom of these of these 4 gates. So whatever value we put here, whatever value we put on here, is going to cause the inputs of these the outputs of these 4 gates will be one of these 4 lines will be turned on depending on, one and only one of them will be turned on depending on what we use as our input. So for example, with the input of 0, 1, that would cause this gate to be the only one that produces an output of 0, 1. Okay, now another piece of electronics we could use is we could take the OR gate that's been knotted and feed its output and inputs into each other. So in this case, the output of, the input of this line, when we set, this is now going to be an interesting piece of electronics. When we put a 0 here and a 1 here, if you follow the inputs, this 1 being ORed together with anything here, it doesn't matter what this line is, will produce an output of 1. This NOT bit will flip it back to 0 and put it in here. These 2 zeros would then produce an output of 1, and it would stay like this. If we did the same thing by flipping the 0 and the 1, these 2 outputs would reverse the way they are. Here's the interesting thing. On this piece of electronics, here's another copy of it, a second copy of it. If we put an input of 0 and another input of 0, what would happen? Well, this 0 would not let us know what the output of this OR gate is, so it really depends on what this purple line is. And whatever this purple line is, that would be its output, and then this would reverse it and change into the black line. So the purple and the black are opposites of each other. One is a 1 and the other one's a 0, or vice versa. And that's what the outputs of these things will be. But the interesting thing is that when we set this to 0 and 0, what values would the purple line and the black line be? It would be whatever values they were before we set it to 0, 0. So what's important about this piece of electronics is we have the ability to set the value, and then we have, oh, sorry about that. Okay, we have the ability to set the value up here by using an input of 0 or 1. We have control of what these two output lines are. So in other words, a 0 and a 1 here will cause a 1 to come out here and a 0 to come out here. And then, and flipping it would flip the values. But then if we decide to take this electronic device and set both inputs to 0, what that will do is cause whatever these lines, the purple and the black line was set to, it will cause those values to freeze. And this is what we're going to use as computer memory. Because what we want to do is we want to store a number into computer memory and then freeze it. If you say a variable x equals 4, we put a 4 into memory and then freeze it so it'll be there later. Temporarily freeze it, I guess I should say. Okay, so now here's what we're going to do. We're going to take a look at 1 bit of memory. Okay, so with 1 bit of memory, we can do this. So this section right here is what we just looked at on the last slide. So this is something that we have the ability to set its value and then also lock its value in. So I'm going to use a 1 to say I'm setting the value. By putting a 1 here means whatever this input line is going to drive the setting of the value. So what we could do is I can say by setting this to a 1, I'm letting this 0 come through here and this 0 now becomes a 1 and drives through here. So this 0 coming in here and this 1 coming in here will cause a 1 to come out of here and a 0 to come out of here. And I just cut this line off because we're not going to care about this. This is going to be the actual value of our memory cell. So on the last slide we had a line coming out of here and here. I just cut that one off. We don't need it. So by setting this to a 1 gives me the ability to put a number here and this will then set this line. Then when I want to set these two inputs both to 0 to lock that value in, I just set the input, meaning save the value, and then at this point the input doesn't matter because once this 0 goes through here, both of these AND gates produce zeros, so the zeros are going into that flip-flop thing we had before, and the value gets saved. So if we wanted to write, this is a 1 bit, a piece of memory that's size 1 bit. If we want to write the number 0 into the memory cell and then lock it in, we put a 0 and a 1 here, allow some time for the electricity to propagate through, and then set this one to 0, and it doesn't even matter what this one is, and then it'll just lock on 0. Okay. So now if we wanted to address memory, what we could do is, let's say we had 4 pieces of memory that we wanted to write somewhere into another piece of memory. So suppose we wanted to take a copy of the value of, let's say, out of the 4 inputs, A, B, C, and D, we decided I want to take this memory location. So this is now what we had on the previous slide. This is now memory location with an output coming out, and let's say the values for A, B, C, and D are locked in. A, B, C, and D are equal to either 0 or 1. If we made a decision that we would like to have, let's say this is the 0, 0 memory location, this is 0, 1, this is 1, 0, and this is 1, 1. I wanted to take the value of the B and have it drive through this and copy to another memory location. What we can do is we can put a 0 and a 1 here, which would cause, out of these 4 gates, a 0 and a 1 here would cause this one. This is now a 3 input AND gate. The 0 going into here flips over and becomes a 1. This 1 going straight into here becomes a 1. And then whatever the value is along this blue line will be the output of this gate. And that will propagate into here and then propagate out. This setting here caused this gate, and this gate to all output zeros. So what we really did was we had, out of these 4 inputs going into these 4 gates, with this value we shut off 3 of them, this one, and this one, and only left this one open, and that's how this value got traveled through and all of these got ORed together. So the 3 zeros and the blue line got ORed together. Okay, so now what we're going to do is we're going to take a look at addressing a bigger scale of memory. So we talked about a decoder. The decoder was the thing where you put in 2 input bits and then one and only one of these 4 lines gets electricity flowing on it, and the other 3 have no electricity flowing out of them. So suppose we wanted to have, so what we're doing in this picture is we have 3 memory cells. These are 3 values where we've set the bits and then locked them by putting a 00 on the inputs. So this is, what we're now going to do, I'm going to use the expression let's say a byte to mean a collection of bits. You know, so you might hear people say, well, 8 bits is a byte, but I just want to say this will be like a nibble, or a collection of bits, bit A, B, and C. So suppose we decided that this group of bits, this is like group number 1, group number 2, group number 3, group number 4. And suppose we decided I want to take this group of bits, and you can imagine this being 8 bits or 16 bits, any group size you want. I want to have this group of bits be transferred somewhere into another group of bits. So let's say, for example, I have a variable A, and this is a variable X, and this is a variable Y, and this is a variable Z in my program. And then I hit a line of code that says A equals X. So I have to go and get the value of A, bring it down to my processor, and then do something with it. So what I'd like to be able to do is, out of these 4 pieces of data, I'd like to retrieve one of them and get one set to be down here. So the way I can do that is I can put the address that I'm interested in on the decoder. So in this case, I put 00. So you run 00 into a decoder, it's going to cause electricity to come out of the 0 line, and no electricity to come out of the 1 line, no electricity out of the 2, and no electricity out of the 3 line. So this electricity going up here and through here, and now we're taking the output of those 1-bit memory cells, the output of these plus the electricity from the decoder makes the output of this AND gate be whatever this value is in the box labeled A. So the box labeled A, its value flows through this wire, runs into this AND gate, and then its value, because this is a 1, continues through here. Same thing is true for the for the B bit, because this electricity on the value of B is flowing through this line. And the same thing is true for the the C line. The value of the C line, along with this being turned on, going into this AND gate, flows through here. As far as the memory cells for the second, the second, third, and fourth byte, their values will not show up in the answer because this electricity being off causes these AND gates to all produce zeros regardless of what the values are in this memory, and a bunch of zeros go down into these OR gates down here. These are OR gates, they're just not drawn like OR gates, because I spun them using Visio. And the same thing's true for here and here. So now what just happened, the transition was we changed the decoder. We said we're now interested in addressing let's call this the first, second, third, and fourth byte. We're now interested in addressing this byte. So by putting a 1 and a 0 here, what have we done? Well, we've shut off this electricity, so now the values of A, B, and C send zeros into these OR gates. But the values in G, H, and I, the G, H, and I cell, those values now go through these gates, and they're listed in blue, meaning they may be 0 or they might be 1, whatever values there are show up. So by putting this number 0, 1 on the decoder, waiting for the electricity to then flow, the values G, H, and I end up showing up down here, G, H, and I. So this is how we address memory. This is how we read from memory. So we're calling this reading from memory. And now if we wanted to write to memory, so really the important things to understand about computer memory is that we are reading from memory and we're also writing to memory. And when we're writing to memory, so these are, again, these are our memory cells. That's the thing we had before where we can set one input to where we could set an input to a 0 and a 1 and then set them both to 0 and remember that value. So what we're doing here is the input going into the bottom of the box ends up being the thing that says a 1 would mean the door is open for an input value to come in, and a 0 would lock it, set its memory. So if we decided we have values x, y, and z, and I wanted to write it into these three cells, this one, this one, this one, and not disturb this or this or this, the way I would do that is I would open the door to this cell, and this cell, and keep the doors for this, plus these 6. I would keep those doors locked. So those would stay, these values would stay whatever value they are, and these 3 values, the door would be open for me to set them. So this would be like if you had an instruction A equals 2. We want to write a 2 into the memory location for A. And let's say these cells right here were the memory location for A. So we want to write X, our goal is to write X into D, Y into E, and Z into F. So we would put on our decoder, which we're now going to call the memory address register. We put a 0 and a 1 on here, which causes, this is the line for 0, 0, this is the line for 0, 1, this is the line for 1, 0, and this is the line for 1, 1. So the 0, 1 line turns on, which causes the inputs of all of these to be set to 1, which means these 3 memory cells are now open to have data written into them. And now what data writes into them? The other bit, the other input bit. So remember it had 2 inputs. One opened the door for it to be set and closed the door, and then the other one was what value if you had the door open. And we just hardwired the X into all of these cells. The X value got hardwired into here, 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 and here. The Y value got hardwired into the second set, and the third value got hardwired into the third set. So this is the way with the 0 and the 1 here, we're opening the doors for those memory cells to take on new values. And so now what just changed is we decided, oh, this should have been a 1 and a 1. So with the memory address of 1 and 1, this line turns on, which opens these cells, and this set of cells are all in memory mode, meaning whatever value was in them stays there. And these 3 cells are now open to accept a new value. Okay, so yeah, sorry, just pretend there's a 1 here. That should be 1. So a 1 and a 1 here means this line is on and these 3 lines are off. And again, this line being off means this memory cell is not interested in taking in its new input. It's going to remember its current value. It's not accepting new inputs. So we have the ability to read from memory and write to memory using the hardware components we talked about before. So inside of here is, inside of this one box, this is a memory cell for 1 bit. There's a lot of electronics in there. Those 2 gates that were feeding inputs into each other, they had knots in front of them, so a lot of transistors and a lot of resistors and a lot of wires just to create a memory location for 1 bit of memory. And then we have to put all this wiring around it just to be able to open up some memory and not other memory. So when we read and write from memory, what we're really doing is, out of our entire memory board, we're picking an address, we're putting bits on an address bus, and we're telling the memory to lock out every memory cell with the exception of the one we're trying to write to. So, with the exception of the one we're trying to write to, with the exception of the one that we're trying to write to, we're shutting off all the other memory locations. So in order to do that, we have to set the fields, the bits we want. We have to allow the electricity to flow through these wires, and then allow a certain amount of time for the data that needs to flow into that memory cell to get there. And then we have to shut things off. So that takes a certain amount of time to read from memory and to write to memory. But what the processor is going to do, in next class we'll talk about how a processor works. The processor is going to read data from memory, maybe perform a computation, and then write results back to memory. So if you had a line that said something like, A equals B plus C, how is that done? Well, the memory location for B is copied from memory to the processor. The memory location for C is copied from memory to the processor. Then a part of the processor, we'll talk about some electronics where we can add two numbers together electronically. Those results will be stored in the processor, and then when that's eventually done, the result gets written back to field A. So that's how we can do A equals B plus C. If you did like in Java code, A equals B plus C, how does that run? On the processor, it would follow that sequence of steps. And the compiler would take the computations trying to make and make it match your computer's architecture. Okay, so is any questions about the